All right, so we've learned about polar bonds, but just because you have a polar bond does not mean that you will have a polar molecule. If you have a polar bond, it means you might have a polar molecule, but you also might not. Let's take a look at some examples. First off, we'll start off with methanol. Structure of methanol is CH3OH, right? And then our skeletal structure is simply that. You can see how those two are the same thing. And then if we were to draw the Lewis structure, we can draw that as well, right? So the Lewis structure is what you should be picturing in your head. We've got this sp3 tetrahedral carbon combined to this sp3 bent oxygen right here, right? And now we can put some dipoles here. Oxygen is more electronegative than carbon, so we've got a dipole facing like this, and then another dipole facing like this. And so our dipoles here are facing the same direction, and so this molecule is indeed polar. And so we can also take a look at a picture of an electrostatic potential map that will show us this, right? So this is what's known as an electrostatic potential map. Where the red represents a lot of electron density. So there's a lot of electrons there. The blue represents low electron density. And then the green is somewhere in between. So you can see that this oxygen is pulling all of these electrons from it, right? Resulting in a zone of very low electron density here and kind of less electron density here as well. And so this is one of the main difficulties with organic chemistry, is that you need to be able to go from this little simple drawing that you're seeing on a piece of paper, and what you need to envision in your head is the three-dimensional structure along with its electronic properties, right? So you need to be able to see this in your mind. And that really only comes through kind of practice. Let's take a look at another example of carbon dioxide. Right, we could draw CO2. And so sometimes this is actually when a carbon has two double bonds, sometimes it'll be drawn as a dot. But we could also draw a kind of Lewis structure here. And so you might be thinking, okay, this is a polar bond, so it's going to be polar, right? The carbon or the oxygen is more electronegative than the carbon. But if you think about it, there's two oxygens on either end, right? So they're both sides here are partially negative. And so there's no net dipole. The dipoles cancel out. And so there's no net dipole, so it's nonpolar. And so the general rule of thumb here is, how do we know if dipoles are going to cancel out, or how do we not know if they're going to cancel out, that kind of thing. So if dipoles face the same direction, they're going to be polar, right? So if you have kind of a dipole that's maybe pointing like this and then pointing like this, right? When they sum together, this is technically vector addition, but really you can just kind of think about it logically, there will be a net dipole. Or maybe in the case of like ammonia, right? They're all kind of pointing upward, right? There'll be a net dipole of pointing upward. If the dipoles face opposite directions, they are going to be nonpolar, right? So if they're facing the same direction, they'll sum and be polar. If they're facing opposite directions, they're going to be nonpolar, right? So if we have these two arrows, kind of like carbon dioxide, they'll cancel each other out and there'll be no dipole. And same thing, if they're facing towards each other, they're still facing opposite directions, right? This one's facing down, this one's facing up. These will also cancel out, and so there'll be no dipole right here. And so overall, this seems relatively simple. One thing you have to really be cautious of is shapes, right? So be careful with shapes. These can really mess you up if you're not careful. Let's take a look at an obvious example, water, H2O. Hopefully you know that this molecule is indeed polar, something you should have learned in Gen Chem. But if you were to just draw this kind of Lewis structure kind of like this, right, that's technically an acceptable form to draw a Lewis structure. You might be thinking that these dipoles cancel out, and then so it'd be nonpolar. But this is wrong, right? This is wrong. And the reason that it's wrong is that we have to think about the shape, right? This carbon in the center is sp3 hybridized, and so it has a bent structure, right? A molecular bent structure, or the tetrahedral electron structure, right? So the real way to draw water is something like this, where one of these lone pairs is going in the board, one's going out. And so you can see these dipoles now face approximately the same direction. And so there's a net dipole pointing up. And so it is polar. Another example, triethylamine. This is the correct structure for triethylamine. A little bit different. Right, that's the correct structure for triethylamine. And so you might be thinking, all right, well, all of the dipoles are facing the same direction because carbon is more nitrogen is more electronegative than carbon. So you might be thinking it's nonpolar. And again, this is wrong because you're not thinking about the shape of the compound. This nitrogen, in order for it to be neutral, there must be a lone pair there. We don't have to draw the lone pair, but it's still there, right? So this is an sp3 hybridized carbonyl or nitrogen, and it's trigonal pyramidal, right? Trigonal pyramidal. And so kind of the correct way to kind of draw this would be this nitrogen here, and then there's a bunch of carbons, right? So I'm just gonna write them like that just for now, right? One's coming out of the board, and then one's going back into the board. And so now we can see that these dipoles are actually all facing the same direction. They're all facing approximately upward. And so there is a net dipole here, and this molecule is indeed polar. So here's just a table from your book that shows different compounds and their dipole moments, right? A bigger dipole moment means a more polar molecule, right? So you can see something that's like sodium chloride, very ionic, very polar. C2H or CH2O, think about what the Lewis structure would be here. This is actually formaldehyde. So it's something like this, right? So there's a net dipole right there, right? We already covered water, methanol. We saw an example of that. This guy right here is acetic acid. So it looks like that, right? There's a net dipole there in between the two oxygens, right? We covered ammonia here. You can see here's proof that carbon dioxide is indeed nonpolar. And all of these carbon-based, carbon-hydrogen-based compounds are also nonpolar. And so we as organic chemists, what we do is an organic chemist looks at a bunch of lines and letters, right? Because that's essentially what these skeletal structures are, and sees a molecule and its properties. Right, so we see these lines, but we know what they actually represent. They represent these complex molecules, and so we see what they really are, right? And so my analogy here is that's kind of like the Matrix. If you haven't seen The Matrix, it's a great movie. You should go check it out. But basically what the main plot line is, they live in this kind of computer world, and they go into this kind of computer simulation. And there's this one guy that basically just kind of keeps track of everything. And so what he's doing here is he's looking at a bunch of code on this computer, right? All these kinds of lines and letters. But what he's really seeing is, you know, what's going on, right? There's a simulation of a person. maybe the person is next to kind of a house or something, and then, it's bright and sunny out there, right? Just how this matrix guy looks at this code and sees this kind of real life scenario. We look at these letters and these lines. We look at these letters and these lines, and what we see is a complex molecule. It's three-dimensional structure, but also its properties, its electron density, and all kinds of cool stuff. Next up, we'll see how we're going to use these things that we've learned to predict what these molecules are going to do.